we're going to discuss about the time reversal. Okay, so the idea is to see what happens with a Markov chain if we look at this Markov chain backwards in time. Okay, so let's start with a simple example. So let's look at the random walk on the circle. Okay. So we start with, let's look at the random walk with probabilities 1/2 and 1/2. Okay? And we number the sites in some way. So if we run this Markov chain for a while, we will see a trajectory. Okay, so for example, okay, so let's do a simulation. So that's the best thing to do. So I'm going to use the random simulation number, random.org. Okay, so let's say that we start at 1, and then I'm going to simulate the jumps here on the simulator. Okay, so we get this trajectory. So this is a possible trajectory, no? Turns out that so let's look at the inverse trajectory. What is so what is the probability to see this trajectory? Ah, e por que 2 elevado a menos 11?
Porque seria... são 10, tá? 2 elevado a menos 10, desculpa. Seria, para cada uma das arestas tem 50% de chance dele ir para aquela escolhida. Porque todo mundo tem temos escolhas, ainda não demos.
So, one claim is that the probability of seeing this trajectory is 2 to the 10. Do you agree?
É.
So then, what is the probability?
Cinco vezes
So the first proposition is 1 to 2 to the 10. Okay, so there is another proposition. You were saying something else. 2 to the 1 to the 2 to the 9. Right? Because 1 to the 9 because there are actually 9 transitions here. There is another proposition which is 1/5 times 1 to the 9. And why 1/5? Because the probability of this guy being equal to 1. Okay, so actually at the same time, all of these numbers and none of these numbers are correct. Okay? Because I haven't specified what is the probability to start from 1. So let us remember that a Markov chain has 3 parameters, right? The state space, the transition probability, and the initial state, the initial measure, the initial probability configuration. So here, in principle, so the question here is, what is the probability of seeing the trajectory and the trajectory is 1, 2, 1, 2, 3, 4, 5, 4, 3, 2. And the answer is the probability of starting at 1, which has in this problem here hasn't been specified yet, times 1 over 2 to the 9, right? Which is the probability of making at each step the right transition. And now another question, which is the following. Okay, so this is not what I wanted to ask. So now the question is slightly different. So we have to imagine this Markov chain as a sort of movie or audio or something that goes with the flow of time. Okay, so we simulate this chain, let's say, and we see the trajectory going on time. And now we stop and we do the following. We reverse the movie. So we can play it backwards. No? We have this media file and we play it backwards in time. And we want to try to see whether what we see is also, I mean, the question is, what type of stochastic process do we see when we reverse a Markov chain? Okay, so we take a Markov chain that does these Markov chain things, and then we reverse it. Okay, so we play it backwards. And then the question is, what do we see? Okay. So what is the probability of seeing this trajectory here when we play the movie backwards in time? So now the question is, if we play the chain backwards in time, what is the probability Two, three, 4, 5, 4, 3, 2, 1, 2, 1. So what is the answer? So proposition is mu2 is 1 over 2 to the 9, right? Okay, so do you agree? Do you disagree? It's the same, exactly. Of course it's the same, no? I just told you, no? You run your Markov chain and you play backwards in time. The probability of seeing the backward trajectory is exactly the same of seeing the forward trajectory. Então, a answer to this is the same. It is mu1 times 1 to the 2 to the 9. Why? Because, yeah, I mean, you have to think about it, no? First you run a simulation or a stochastic procedure, then you reverse it in time. And I'm asking, what is the probability of seeing some reverse trajectory? It's exactly the same as seeing the non-reverse trajectory. Yeah?
Mas mesmo se o MID 1 for diferente do MID 2?
Mesmo. Porque o que eu estou dizendo, olha o que eu estou dizendo, eu não estou perguntando qual é a probabilidade de ver essa trajetória na cadeia de Markov. O que estou perguntando é, vou rodar minha cadeia de Markov 10 vezes, vou pegar essa sequência, vou reverter, e a pergunta é, uma vez que fizer isso, qual é a probabilidade de ver é isso aqui. Então, como que eu construí essa sequência aqui? Eu primeiro joguei 1, depois joguei todos os números para trás. Então, a probabilidade é μ1 vezes a probabilidade da trajetória, das transições. Não é... Eu não estou... É diferente de perguntar qual é a probabilidade de ver isso aqui desde o início. So when I say reversing time, so you have to imagine a movie, okay? So I play. This is a random movie. I play it forward. We know we know what is the probability of seeing a given sequence of images, right? Because it's just a Markov chain. So it's the probability of seeing the first image and then seeing all the transitions seeing all the correct transitions. Now I say the following: take these images, put it backwards in time, and play it now. What is the probability of seeing that sequence? It's the same because the stochastic procedures is still the same. It's different. The question will be different instead tell you what is the probability of seeing this sequence from the beginning. It's not the same. Yeah? Exactly. So yeah, so the first question, okay, so as he pointed out, is the first question is what's the probability of x0 being equal to, so it's it's 1, x1 equal to 2, x3 equals to 1, etc. No? And this is the probability of seeing 1 times 1 to the 2 to the 9, which is actually. And the second probability that I ask you is what is the probability of x9 being equal to 2, x8 equal to 3, etc. x1 equals to 2, and x0 equals to 1, no? Which is, of course, exactly the same. No, because I'm asking exactly the same question in terms of probability. I'm just writing in backwards. Yeah. So now, but on the other hand, if you look at this dynamics, if you look at backwards in times, we are tempted to say that it's the same, right? Because if you are here, it means that the previous step, in the previous stage, you were here or here, and the probabilities are also 1/2, 1/2, right? So if you know that you're here at step, let's say, n, you know that you were here at step n minus 1, or here at step n minus 1. But in order to so now the observation I want to make now is the following. So the probability of seeing the trajectory 3, 4, 5, 4, 3, 2, 1, 2. So this is okay, this is effectively mu2 times 1 to the 2 to the n. Right? Because if I ask you what's the probability to see this trajectory when you play forward in time, so when you play it at the right time direction, well, it's the probability of seeing the first guy here too, and then to make all the right transitions.
Because you're missing a 1 at the end.
Maybe, yeah, thank you. So here we are tempted to say that, well, if mu1 is equal to mu2, something interesting happens, no? And this is something one can check, actually. Okay? So, I'm going to leave it as an exercise for you. So, exercise. So now we are going to take this Markov chain only up to a finite time big T, and maybe I'm going to call it T because T from time. So so this be a symmetric simple random walk. Remember that SSRW means symmetric simple random walk. Symmetric means that the jump rates are the same to all the neighbors. Simple means that the jumps are only to neighbors. And random walk means what? Random and walk. On the circle, let's say ZP, okay, with some P integer number, positive integer number. With uniform initial law. Initial law. Okay, so just to remind you, we have the how do we characterize a Markov chain? So we say that a certain Markov chain is so a certain stochastic process is a Markov chain with state space omega transition matrix P and initial law mu if for every t in this case here, I'm not defining that up to infinity, only up to time t, big T. No, it's not a problem. For every sequence of length t plus 1 in omega, the probability of seeing the trajectory little x0, little x1 up to little xt is given by the chain formula. So it's the probability of seeing the first guy times the probability of seeing the right transitions. Okay? So this is can be taken as a definition of a Markov chain. So if one wants to prove that something is a Markov chain, one has to prove this identity here. Okay? So the idea is that if we choose the initial point of our Markov chain uniformly at random, in this case here, and then we run our Markov chain up to some time t, and then we play it backwards in time, what we see as a stochastic process is actually the same process. Okay? Trajectory by trajectory, what we see is different because the probability of the endpoint at which I'm going to reverse my Markov chain being equal to the initial point is not equal to 1. So there is a positive probability of the initial point and the endpoint being different. But in law, the two processes are the same. Why they are the same? Because actually the probability of starting here are ending up here because we're starting the chain uniform. We know that the uniform law is the stationary measure for that chain. So the probability of starting there and finishing here is actually like the same as starting here and finishing there. So now I'm going to repurpose this picture here, and I'm going to do the following. So now the probabilities are going to change. Okay? So I'm going to take 1/3 here and 2/3 here. Okay? So it's no longer it's still the simple random walk on a circle, but no longer symmetric. No? Now it's asymmetric because it jumps with probability 2/3 to the left, it want probability 1/3 to the right. Okay? So
Everything else is kept a half, or is that for every edge?
for every edge.
For every vertex.
Yeah, for every vertex, yeah. So now I'm going to run here my simulation again. Okay, so I start at 1, then according to this guy I go to 2, then to 3, then to 4, 5, 4, 3, 4, 5, 6, 1, 2, etc. Well, I drew. Okay, so let's do this one. Okay, so now the probability, of seeing this trajectory here, x0 equals 1, x1 equals to 2, etc. So the last guy is x9 equals to 1 is equal to what? So it's going to be mu1 times. Okay, so here we have to do a computation, okay, this one is for free, 3 to the 9. And then I have 2 to the number of times I went I did the clockwise, 2 to the 7 divided by 3 to the 9. So that's the probability of that trajectory. So now what is the probability of seeing the trajectory? What the trajectory? So it's 1, 2, 3. So it's 1, 5, 4, 3, 4, 5, 4, 3, 2, 1. Well, the answer is the same, It's the same twice, Because the answer is the same and the answer is the same. But now if I reverse the thing, the probability is 2 to the 2 divided by 3 to the 9, right? Because now in the reverse chain, instead of having 7 steps clockwise, I only have 2 steps clockwise. So you see that the probabilities are different, It's not like when it was symmetric. And this is normal, Because this chain here has a clear tendency to go around. You could see from here, I ran it the very same 10 times, 9 times, I took exactly the same 9 jumps, and what happened is that I did a loop around the circle. So this chain has a tendency to go clockwise around the circle. If we play backwards in time, what we should see is not necessarily a chain, but it is a stochastic process, but a stochastic process that has the tendency to go counterclockwise around the circle. No? If we run this Markov chain here for a while, for some big interval of time interval, in such a way that you take various turns around the circle, when you play backwards, you do various turns around the circle, but in the other direction. So let's imagine that we have some sort of statistics problem. Okay, so I give you a realization of this chain, and you have to decide whether it is the original chain or a time reversal of the chain. How do you decide which is which? So how do you decide if a realization that I give you of this chain is a realization of the original chain, or it's actually a realization of the time reversal of the chain? It's very simple. You just count the number of turns around the circle, counting clockwise, let's say, is positive, and counterclockwise is negative. Now, this is something that people usually, sometimes they call the winding number. Okay, so it's the number of times that you turn around the circle, and if you turn back, you count minus one turn. Right? And but on the other hand, this probability here looks like what you should compute if it were a Markov chain, right? Because it does satisfy the chain formula. No? It is the probability of the first guy times the probability of each transition, but now the transitions are reversed. No, the probabilities are not 1/3, 2/3, are 2/3, 1/3. Right? So now you can have a second version of this exercise, no? Version 2. So what do we do here? We erase the symmetric, no? Ahora it's only simple, it's not symmetric and let's say asymmetric. And if you are super strict about orthography, you have to put an "and" here, no? Okay, so you also have to start uniform, because of the same problem that you had in the symmetric case. And what happens in the asymmetric case is that what you see is a chain with reverse probabilities. What does it mean, reverse probability? It means that these probabilities are exchanged, no? So instead of being 1/3, 2/3, it's 2/3, 1/3. Okay. So if you are here, the probability of going back will be 2/3, and going here to 1/3. It's like taking if you think about it in terms of the transition metrics, the transition metrics with the reverse probabilities is just the transpose of the original metrics. Okay. So now let me do another example. So the state space of this Markov chain is going to be n0, and the probabilities are like this. Okay, so at each point, at its state of this chain, you either go one step forward with probability P, or you go back to the origin with probability 1 minus P. Okay, so this is the chain. Okay, so let's do a simulation of this chain. Always fun to do simulations of chains. So let me do a P equals 2/3, and let me start at 0, okay? So this one went to 0, then to 1, 2, 0, 1, 2, 3, 4, 5, 0. Okay, so this is one realization of this chain. So if we play it backwards in time, okay, this is this is what the chain does. If we play this chain backwards in time, it does something strange, no? Because if you take a trajectory like this and you do it and you put it backwards in time, you will see that what it happens is that when it is at 0, it goes somewhere, and then it comes back one step at a time. It comes back to 0, goes somewhere, and comes back one step at a time. Right? For this one, it's not clear at all that the reverse chain is going to be a Markov chain. It doesn't look very Markovi. How do you decide where you go?
You have like geometric progression. There's like an infinite number of arrows, and the probability of each one, it's like b, and the next one is b squared.
Yeah, okay. And how do you prove that? Okay, so let's see. Why do you say it's geometric?
You can.
Você pode falar português se quiser.
A gente não pode chegar em algum lugar olhando para essa primeira que você descreveu.
Sim.
Se você está no 5, você sabe que o passo anterior ao 4 obrigatoriamente. Então, supondo que você começa do zero, a probabilidade de você ter feito qualquer coisa antes é 1. E se você sabe que daqui a 5 passos é 5, você sabe que você tira a probabilidade P 5 vezes seguidas. Eu estou pensando em como forma.
Uhum. Então, vocês entenderam o argumento? Mais ou menos. Então, o argumento é o seguinte. Se eu vejo no reverso que o cara foi até aqui, é porque na cadeia original, o que ele fez foi avançar K vezes o que acontece com probabilidade P levantado K, e da última vez, em vez de ir para K menos 1, ele voltou para o zero. Isso acontece com probabilidade 1 menos P. Então, o que o nosso colega aqui está dizendo é que tem cara de que a probabilidade com a qual no processo reverso eu vou para um sítio K é uma geométrica. Por quê? Porque esse pedaço aqui, a probabilidade de eu ver esse pedaço aqui é geométrico. Ou seja, a probabilidade de eu ver esse pedaço aqui é justamente a probabilidade de uma geométrica dar igual a 5. Tá bom? Então parece ser bem razoável. Então, so the question here is what does the reversed so idea it jumps from 0 to L in N with probability it's 1 minus P times P to the L. Okay, so this is the proposition. And then it comes back to 0 one step at a time. So
Sorry, I want to understand this. So that is the probability of going to 0 to L, I guess in exactly L steps, and then going back to 0. Is that what you?
exactly.
So when you say one step at a time, you mean in one step, or no?
No, you are at L and then you go to L minus 1, L minus 2, L minus 3. But this is what the reverse chain does.
Reversed one.
Yeah.
Okay.
S-
O problema é que ele pode voltar para zero várias vezes.
So,
This is assuming you start at zero deterministic.
for the moment, we don't know. Okay, so for the moment, I just drew this thing here, and we're trying to figure out how the reverse dynamics looks like, and it seems that starting and ending at zero simplifies things a little bit, right?
Mas ele, professor, ele poderia voltar para o zero várias vezes no meio do caminho, tem que fazer o zero de novo.
Pode, por exemplo, aqui ele volta.
Então são mais passos de geralmente. Esse menos P pode estar elevado a um certo K e aí assim é o P.
Não,
K não.
não. Ah, ok.
Só lembrando que se coloca N e 0 são os naturais, incluindo 0.
Including zero. So now at this point, actually, we need to do some inference, and it turns out, okay. So let me do an observation, okay. About stationary measures, okay. So mu is stationary. This is the general theory, no? With respect to P, if this identity here holds for every x, okay? So what I'm writing here, remember that we say that a measure mu is stationary if mu times p is equal mu. And what I'm writing here is just the identity mu times p equals mu in explicit form, no? So mu times p equals mu is a vectorial identity, so it's an identity that coordinate by coordinate turns out to be this one here.
So that pi should be a mu, or
Huh?
what is pi?
Ah, it's mu, yes. Pi is mu. Yeah, thank you. Okay, so there is this mysterious geometric probability appearing aquí that in principle is reasonable, no? Because the probability of seeing this jump from 0 to y is actually the probability of seeing in the directed chain, in the original chain, 5 forward steps and followed by 1 backward step, okay? Which is exactly this number here. So something that you can check, and now this is for the model that we have there. Mu of L equals, by definition, 1 minus p times p to the L. is stationary. So we have to verify this identity here, okay, for every x. But what does the identity here means? It means that 1 minus p times p to the L, it's equal to what? So you have to go from y to x. So if x is different, let's assume that x is different from 0. So if x is different from 0, the only way on which you can arrive to x is from x minus 1. Right? Because you go one step forward and otherwise you go back to 0. Okay? So this is actually equal to p times the measure of L minus 1. So it's the probability of going from L1 to L times the measure of the point L minus 1. So you see that then this is true for every L bigger or equal than 1. Okay? Observe that I don't really need to verify this identity at L equals 0 because one of these identities is for free. Right? Because the sum is a probability measure. So if you sum over x here, you get 1 because mu is a probability measure, and if you sum here over x, you get 1 because p is a stochastic matrix, and once you have 1 here, you sum over y and you get 1 again. So if your state space has n points, there is actually n minus 1 equations here. In this case here, the state space is infinite, so you still have infinite equations, but if all of them except one are satisfied, the last one has to be satisfied because of they are not linearly independent, no? These equations are not linearly independent because there is a relation between them, no? The sum is 1. If you sum in all these equations on the left hand side you get 1, and on the right hand side you get 1. Okay? So we do not need to verify L equals to 0. Okay? So that's this a little bit mysterious. A little bit mysterious probability that appear there, the geometric law, is actually the stationary measure of the chain. Okay, so that leads us to some definitions. Okay, so the definition is the following definition. So let P be irreducible So let me, okay, let's call it mu. Okay? So we are going to assume either that P is finite or that it has a stationary probability measure mu. Actually, this is redundant. It's a little bit redundant because if it's finite, if the state space is finite, then it has a stationary measure mu. But if the state space is infinite, it's not necessarily true that the stochastic matrix P has an invariant probability measure. Okay? We saw the example of the random walk on the integers. So the random walk on the integers has a stationary measure, which is the uniform measure, the counting measure, no? The measure that gives weight 1 to all points on the integers, but it's not a probability measure, and it's not normalizable. No, you cannot divide by the total mass to get a probability measure. This is not the case when gamma is finite. When gamma is finite and P is irreducible, we always have a stationary measure, and this stationary measure is moreover unique. One property that we saw, I probably just mentioned it, but it follows from the considerations we had, is that the stationary measure mu has full support, meaning that the mu of x is strictly bigger than 0 for every x in omega. Okay, so I'm going to write down here. This is an observation. If P is irreducible, and pi P and mu is stationary, probability measure, then mu of x is strictly bigger than 0 for every x. Okay? The reason for that is that remember that we saw that there is a power of P that has all entries positive. So all entries of P to the we call it big N, I think. P to the big N is always, all the entries are positive. So if you multiply any probability measure from the left by this matrix that has all entries positive, then the resulting vector has all entries positive, right? Because this probability measure will have one entry positive that is going to be multiplied by a positive entry of the matrix, and then the result is going to be positive. Yeah?
Yeah, for that theorem, they want to, if it's aperiodic, right? It's aperiodic, then P to the n positive for some n. You assume the state space is finite, right?
It's finite.
So you take the maximum. So is that also here an implicit assumption in the observation?
No. If the space state is infinity and you have a stationary probability measure and it's irreducible, then the probability also has to be positive.
What would be the proof in that case?
The proof is basically the same, in the sense that so you have a path that goes from x to y, then you multiply by mu X has positive probability, and the I entry has to be positive because there is a path.
Right.
Okay.
Okay.
And here I forgot that this is also true. I forgot here to put an aperiodic. No, I always forget about the other. Okay, so for me all matrices are always aperiodic. Because if they are not aperiodic, it's too annoying. So here is also an aperiodic. Okay. Well, you don't need a here aperiodic in this definition here.
Your observation, you also didn't use a periodicity, right?
I also didn't use a periodicity. Yeah, I used it in the proof that I was describing, but you can tweak the proof to cover the periodic case, the non-periodic case. Okay, so this condition is going to be important for this definition that I'm going to do now, because so this is sometimes called the time reversal of P is the matrix P hat given by this is for every x, y, over. Okay? So you see that in this definition, it's very important that the measure has full support, meaning that mu of x is bigger than 0, strictly bigger than 0 for every x in omega. Because otherwise, you cannot do this definition. Right? So this is not well defined unless mu has full support. Então, so this is the definition of the time reversal. And the proposition is that P hat is a stochastic matrix. Okay? So proof. Well, a stochastic matrix is a matrix with entries which are all non-negative, such that the sum over each row is equal to 1. Okay? So here the entries are clearly non-negative because these numbers are all non-negative here. Okay? So that's something we don't really need to care about. So the only thing that we have to verify is that the sum over the rows is equal to 1. Okay? Yeah. So the sum so we have to do this. Right?
Isso não é.
So now you see why I remind you about this observation here, right? So the sum that appears there is exactly the sum No? This sum over y is equal to this sum over y here. So it's equal to mu x. So this is actually equal to mu x divided by mu x, because mu x gets out of the sum because it's constant in y, so you get 1. So that shows that the matrix P hat is stochastic matrix. And now we can state our main theorem of today, which is called the time reversal chain theorem. So the time reversal chain is the following. So let P Yes, of course. Thank you. Okay, so what happens is the following. So we have this is what we sometimes call a stationary Markov chain. Okay? So it's stationary because the initial condition is a stationary distribution, and since the initial condition is a stationary distribution, then the law for any fixed time t is a stationary distribution. Remember that the law of the vector, of the chain as a vector, can be very complicated. Okay, it's only the marginals that they have this law mu. Okay, that's what we call stationary. It's different from IID. Okay, but stationary, we take as a stationary Markov chain, we run it for a time until time t, big T, And now that we have drawn it to time t, we take the time reversal. Okay, so we look at these random variables the other way around. We flip the vector like that. And what we see in that case is a Markov chain. It's also a stationary Markov chain. The stationarity is clear because if a vector, if I read the entries of a vector in this direction, and all the entries has the law mu, then when I read the entries of the vector in the other direction, all the entries will also have law mu, because the law of each one of the guys didn't change. What might have changed is the relation between the coordinates, because I'm reading the coordinates in a different order. And what happens is that when you read the coordinates backwards in time, what you see is effectively a Markov chain. This is highly non-trivial, okay? Because when you look the chain backwards in time, so what does it mean to be a Markov chain? It means that the future only depends on the present. But when you look the Markov chain backwards in time, what you know is that the past depends only on the present. And why also the future depends only on the present? That's a computation that has to be done. Okay, and this is why this is a theorem. And it only works. It works only in two cases. When the initial condition is the stationary measure, and when you start at and end at the same point. Okay, this one I'm just telling you. We're not going to see it today. We're going to see it tomorrow. For the moment, we are going to be satisfied looking at this. Okay, so what happens is that the reverse chain is still a Markov chain, but the matrix changes. Okay. Notice that if the measure mu is uniform, then this ratio here is 1, and the time reversal matrix coincides with the transpose. In the first examples I gave you, the examples of the simple random walks on the circle, that was the case actually. No, the invariant measure was uniform, and then the time reversal is just a transpose. Notice that if you have a stochastic matrix and the transpose is also a stochastic matrix, it means that the columns of the original stochastic matrix add to 1. So this is what we call doubly stochastic. Okay, so a matrix is said to be doubly stochastic if the sum over rows is equal to 1 and also the sum over columns is equal to 1. In that case, automatically the uniform measure is stationary, right? Because something which is true for every stochastic matrix is that you multiply from the right by the vector 1, 1, 1, 1, 1, 1, 1, you get 1, 1, 1, 1, 1, 1. No, because this is exactly the condition of the rows add up to 1. That means that when you take the transpose, this vector here goes to the other side, no? To the left. And then the relation becomes the vector 1, 1, 1, 1, 1 is an eigenvector of the matrix. So if the matrix is so you can check that the uniform measure is stationary for a stochastic matrix P if and only if it is doubly stochastic, meaning that the transpose is also a stochastic matrix. In that case, the time reversal and the transpose coincide. In the time reversal, there is always a transpose, no, involved. right? Because this guy here is a transpose of the matrix P. But you have to correct it by the invariant stationary distribution.
E aí a cadeia ela vai ser reversível necessariamente. Não necessariamente será.
Esa é a definição que vem agora. And so I'm not going to prove this theorem because the proof is actually it's just the generalization of the exercises that I gave you before, no? So if you do the exercise, then you can do the theorem. And also you can, if you don't want to do the theorem, you can read the proof of in any of the references that we have. Okay? So so that now there is an important definition, okay? Which is the following. So we are still in the context of the theorem, therefore in the definition here of time reversal, which means that we are going to assume that that P has a stationary measure, okay? And it's irreducible. So P is irreducible and it has a stationary measure. So the definition is the following. So we say that, P is reversible if the time reversal is equal to the original matrix. Okay? So this is the definition. So as you may have already noticed, so whenever you have an identity like this is a matrix identity. So you can write it coordinate by coordinate, right? And sometimes the matricial notation is more useful. Sometimes the coordinate by coordinate notation is more useful. And the coordinate by coordinate notation is this one here, no? And what we do is just multiply by mu x to have a nicer formula. And this is true for every x and y in omega. Okay? And this thing here has a name. Detailed balance. Sometimes it's called detailed balance condition. Sometimes it's called detailed balance equations, depending on the author, but both mean the same thing. So this is the definition of reversibility, okay? So what does it mean from the point of view of a Markov chain that the Markov chain is reversible? So if you take a Markov chain associated to the transition probability P, and you start the Markov chain with the stationary measure mu of this transition matrix P, what happens is that the time reversal has the same law as the original chain. So the chain and the time reversal, from the statistical point of view, are indistinguishable. So now if I give you a sample of the original Markov chain, and then I give you a sample of the time reversal, so I take it and just I reverse it, the vector, there is no way that you can tell me whether it was the original chain or the time reversal, because both has exactly the same law. So the simple random walk on the circle is reversible if and only the probabilities are symmetric. Okay, so the probabilities are 1/2, 1/2. So these are the questions that one has to solve if one wants to find a stationary measure, right? So these equations are difficult to solve, right? Because so let's imagine now we have a complicated problem. It is very easy to be faced with a Markov chain that has something like 2 to the 64 states in that state space, right? So there is something called the Ising model. So you can check. This is a checkboard basically. I mean, it's an 8 times 8 grid. And in the Ising model, what you have are pluses and minuses, and on each
Na segunda linha,
okay. Thank you. So the basic model or other models based on this thing, there are many Markov chains that you can define on this state space. Okay, so this state space is what? It's the so if you call lambda n this set here, the state space for this chain here is just 0, 1 to the power lambda n times lambda n. Okay, so there are 2 to the n square possible ways to put pluses and minuses on this grid. So this is an 8 times 8 grid, so the number is 2 to the 64. So 2 to the 64, as you can imagine, is a huge number, no? 2 to the 10 is 10 to the 3, so 2 to the 60 is 10 to the 18, so 2 to the 64 is something like 10 to the 20. So 10 to the 20. So good luck trying to list 10 to the 20 configurations on even a computer, a powerful computer. So if you define a Markov chain here with this state space in some way, there are many ways to do that. If you want to find an invariant measure, you need to solve these equations here. So 10 to the, how many is this? 10 to the 20 equations. How do you solve 10 to the 20 equations? You cannot do that. Okay? Even to verify that a given measure is an invariant, is an stationary measure is difficult, no? Because even if I give you the measure, then you need to come here and verify 10 to the 20 equations. I mean, these huge sums there. Hã? Mesmo o computador não dá.
Ali seriam números binários de 64 bits.
Exatamente. Então, o número binário de 64 bits está bem perto do que o... E está bem perto do que um computador consegue... E se você achar que dá... Hã?
Eu pensei em comprar algum cluster de uma database ou uma coisa absurda, e não foi tudo normal.
Você vai conseguir.
Aí eu vou conseguir.
E se você conseguir... eu só botar aqui mais exatamente.
Eu levo do pai à falência.
Claro. Mas... But in the other hand, these equations here are very easy to verify, right? Because just involve identity between two numbers. I mean, you need 4 numbers, no? So here there are lots. There are n square equations. So there are way more equations. There are n squares. So if the size of omega is n, there you have n equations with n variables on each equation, no? Here you have n square equations, but they have only 2 variables, so these are much easier to verify. But reversibility is a very particular property. Okay, not all chains are reversible. Many chains are non-reversible. So let me give you so what do I want to do now? Okay, so maybe I leave the examples for tomorrow. See?
Vou fazer uma pequena viagem. Você conhece causalidade?
Uhum.
Causal. Isso basicamente é um baita help, né? Você saber de onde você, dado que você está hoje, você saber de onde você veio. Quais devidas probabilidades. Saber o caminho reverso. Seria até muito útil se você modelar
O problema
gráfico.
o problema é que você não sabe o caminho reverso, você sabe a lei do caminho reverso.
Entendi.
Mas tem gente que faz isso, não? Coisas do gênero são usadas em reconstrução de imagem, né? Tem uma coisa que é bem popular hoje em dia em reconstrução de imagem que se chama diffusion method. E diffusion method é basicamente isso aqui. supor que a imagem foi construída com uma cadeia reversível e você rodar a mesma cadeia para completar a imagem. So, what I want to say? Yes. So, not all chains are reversible, no? Because this condition is stronger than the condition of stationarity. So here we have n square. It's not exactly n square equation. It's actually n times n minus 1 divided by 2, because if you take x equal to y, this equation is trivial. And then if you take x equal to y and y equal to x, is the same equation. So you have n minus 1 over 2 equations. So it's a very over specified system as a system of linear equations, no? Because I have, if I see this equation here, the tail balance, no, as an equation for mu, I have n minus 1 over 2 equations for n minus 1 variables, no? It's not n variables because we know that the sum is 1. So there is if you know n minus 1 of them, you know the last one. So we have here n minus 1 variables and n times n minus 1 divided by 2 equations, which is way bigger than n minus 1. So it's overdetermined, and in particular it doesn't have a solution. Okay, unless something very special happens. So among the universe of Markov chains, the set of reversible Markov chains is a very small set. But you probably know about something called Markov chain Monte Carlo. You heard about it. And in Markov chain Monte Carlo, you take the opposite point of view. If I give you a measure, so I give you a measure mu. Why? Because, yeah, why not? And I think about the problem of finding a Markov chain that has this invariant, this measure mu as a stationary measure. I can look at these equations, and these equations are actually the opposite, no? They are underdetermined, no? Because if I look at these equations here as equations for the entries of the matrix P, what we have is n times n minus 1 over 2 equations for n times n minus 1 variables, no? Because so the sum of the rows is equal to 1, so I can assume that so the last column is not is already determined by the previous columns. So this is so if I want to determine, if I want to find a stochastic matrix P, I have to find n times n minus 1 entries of the matrix, and this thing here provides me with n times n minus 1 divided by 2 equations, which means basically that if I give half of the matrix, the other half is determined by this equation, right? So if I give you if I give you the entry here will be automatically determined. The only restriction is that they had to add up to 1, so the last column has to be positive. So from this reversibility, from the detailed balance equations, and this is how physicists actually used to begin with this detailed balance equation. So detailed balance is the physicist name for these equations, okay? And they thought about these equations the other way around. Okay, so These are equations not for mu but for p. And so problem given a measure, probability measure, okay, mu, find a stochastic matrix such that mu p is equal to p. Okay, as a stochastic matrix, maybe let me call it p. Okay? So this is a problem. And if one is faced with this problem, this thing here may help, no? So answer and this answer is called Glober dynamics. It's called Glober dynamics or not? Let me remember. Well, I call it whatever I want. Yeah. So in some particular cases, it's called Glober dynamics. Glober, Nobel Prize in physics. Okay. So what you can do, so you want to guarantee that this is always satisfied, right? Well, you can fix one and get the other. There is a restriction that these numbers have to be smaller than 1, right? So how do we guarantee that these numbers are smaller than 1? There is a clever way to do that. One possible way is to define the following. So let's define pxy. So if you do this, then this is automatically satisfied, no? But there is a problem, no? What is the problem? Huh? Exactly. It doesn't add up to 1, right? So how do we solve that problem? So it doesn't add up to 1, and the problem is not that the sum is smaller than 1, but it's that it's bigger than 1. No? For example, let's say that mu is uniform. Then this is 1/2, and then the sum is clearly not going to be 1; it's going to be n divided by 2. So it's super big. Okay, so something that you can do is that you can multiply here by a constant that I'm going to call z. Okay, and then I want the sum. So we want that the sum over y of pxy is equal to 1. Okay? Observe that this equation here it's only for x different from y, right? Because for x equal y, this equation is identically satisfied. So there is no equation for xx. So this is what we want. Okay? Yeah?
Então, desculpa, não seria resolvível por alto valor à direita? Esse MIP igual B?
Não é o único possível. Tem vários. Essa aqui é que se chama Escola de Glauber.
Tá, beleza.
So we want this, okay? And notice that if this number is always smaller than 1, then we can always choose pxx as 1 minus this number. So we choose, so the first thing we do is that we choose p xx equal to 1 minus the sum over y different from x of pxy, and so this is why notice that I can multiply by a constant 1 over z here, no? And so now what is the constant that I'm going to choose here? I'm going to choose a constant in such a way that this sum is always smaller than 1. So that means to take z equal to the maximum over x of the sum over y different from x of mu x divided by mu x plus mu y. Okay? So if one does that, then we found a way to define a matrix P in such a way that the invariant measure is mu. Okay? So in particular cases, there are ways which are more efficient, but this is one possible way to do it. Okay? So this is so this is like a baby step into MCMC. Okay, so into Markov chain Monte Carlo. Okay, very good. So tomorrow I'm going to give some examples of the. So what I'm going to do tomorrow is that I'm going to give you examples, okay, of various things. I'm going to talk. If you look at the book, you probably notice that I skipped the part about heating times. Okay. The Sumit Pal. So this one. No? So I skipped the part about heating times. I'm going to go back to that. But what I wanted to do, so next week there is the first exam, right? On Thursday. So my plan is to start to talk about heating times on Tuesday. So there won't be heating times on the exam, okay? Because heating times is kind of it's a complicated subject if you have never seen it before. So what I did is that I did a little bit of reshuffling in such a way that heating times doesn't enter into the exam of Thursday. Okay, so I'm skipping heating times. I'm going to go back to heating times, but heating times won't be part of the first exam. It will be part of the second exam. So then we will have a little bit more time to study about it.
It's going to be 2 or 3 exams?
3.
It's going to be 2 hours of the exam.
I will give you details, more details on Tuesday.